Let's try the shortest path algorithm on a much larger graph. Let's start at London. London's neighbors are Amsterdam and Paris. The distance to Amsterdam is 4, and the distance to Paris is 3, and we add them to the tree. The next node in the table is Amsterdam. Amsterdam's neighbors are Brussels and London. The distance to London via Amsterdam is 4 plus 4, or 8. London already exists in the tree, so we compare the calculated distance to the existing distance, which is 0. 8 is greater than 0, so London's distance stays unchanged. The distance to Brussels via Amsterdam is 4 plus 3, which is 7. We add Brussels to the tree. The next node is Paris. Paris's neighbors are London, Brussels, Milan, and Barcelona. The distance to London via Paris is 3 plus 3, which is 6. London already exists, so we compare 6 to the existing distance, which is 0. 6 is greater than 0, so London's distance stays unchanged at 0. The distance to Brussels via Paris is 3 plus 3, which is 6. Brussels already exists, so we compare the calculated distance to the existing distance. Since 6 is less than 7, we have found a shorter distance to Brussels. We're going to update the Brussels node in the tree. The distance to Milan via Paris is 3 plus 5, which is 8. Milan is new, so we add it to the tree. The distance to Barcelona via Paris is 3 plus 8, which is 11. Barcelona is also new, so we add it to the tree. The next node is Brussels. Brussels' neighbors are Amsterdam, Paris, and Munich. The distance to Amsterdam via Brussels is 6 plus 3, which is 9. Amsterdam already exists, so we compare the calculated distance to the existing distance. 9 is greater than 4, so Amsterdam's distance stays unchanged at 4. Clearly, it is faster to go from London directly to Amsterdam, rather than going to Paris, Brussels, and then Amsterdam. The distance to Paris via Brussels is 6 plus 3, which is 9. Paris already exists, so we compare the calculated distance to the existing distance. 9 is greater than 3, so Paris's distance remains unchanged at 3. The distance to Munich via Brussels is 6 plus 6, which is 12. Munich is new, so we just add it to the tree. The next node is Milan. Milan's neighbors are Paris, Munich, and Barcelona. The distance to Paris via Milan is 8 plus 5, which is 13. Paris already exists, so we compare the calculated distance to the existing distance. 13 is greater than 3, so Paris's distance stays unchanged at 3. The distance to Munich via Milan is 8 plus 3, which is 11. Munich already exists, so we compare the calculated distance to the existing distance. 11 is less than 12, so we have found a shorter distance to Munich. Thus, we update the Munich node distance and parent. The distance to Barcelona via Milan is 8 plus 7, which is 15. This is more than the existing distance, which is 11, so Barcelona's distance stays unchanged. The next node is Barcelona. Barcelona's neighbors are Paris and Milan. The distance to Paris via Barcelona is 11 plus 8, which is 19. 19 is greater than 3, so Paris stays unchanged. The distance to Milan via Barcelona is 11 plus 7, which is 18. Milan already exists, so we compare the calculated distance to the existing distance. Well, 18 is greater than 8, so Milan stays unchanged. Finally, we have Munich. Munich has two neighbors, Brussels and Milan. The distance to Brussels via Munich is 17. 17 is greater than 6, so Brussels stays unchanged. The distance to Milan via Munich is 11 plus 3, which is 14. 14 is greater than 8, so Milan stays unchanged. Here is the final shortest path tree. For example, the shortest distance from London to Brussels is 6 via Paris, and the shortest distance from London to Munich is 11. But there are two nodes in between. There's Milan, and if we look at Milan's parent, it's Paris. While we started at London, we did not specify a destination. That's because regardless of the destination, the shortest path algorithm requires us to inspect every reachable node from the origin. In addition, this algorithm finds the shortest path to every node from the origin. Here's a video demonstration of the algorithm. We have found the shortest distance to every city, but what if we are interested in finding the path that consumes the minimum amount of energy, or the least expensive route? These can all be calculated by changing the edge weights to energy needed between cities, or the cost to travel between cities.